find phi such that phi xx plus phi yy equal to a 0. So I conjecture that that's a reasonable guess because we know that the argument is a solution. And we know that the argument's constant on rays from the origin. And we also know that if we shift, first of all, if we rescale a function, it's still like if a function is a solution of Laplace's equation, a real multiple of the function is still a solution of Laplace's equation, right? And as you guys have experienced in finding the harmonic conjugate, there's always a freedom to shift by a constant, an additive constant, right? So if we start with something we know is a solution to Laplace's equation, we multiply by a number, we add a number, we still got a solution to Laplace's equation. But now we've got the freedom to fit this data. See, because we know that phi of, let's say R is equal to A plus B argument of R. And here I'm just saying, like, this point down here is like R. This point up here would be R e to the I pi over 4. Right? So in other words, just a real input. What's the argument of a real number? Well, it's 0. So this is equal to A, because this is 0. And so I wanted this to also be equal to what I was trying it to be, 10. Okay, so set that equal to 10. Apparently A must be 10. Hooray! All right, great. And also, phi of anything on this ray, right, e to the, and you don't have to do an arbitrary point, right? You could just feed this 1. It would be, you guys, if you don't like R, you could just put 1 in here. And you could just put, e to the pi I over 4 in here if you prefer not to mess with the R. I'm just saying an arbitrary point on the ray has to map to 10 and 20 up there, right? But so this is equal to 10 plus the B we don't know yet. Argument of, e to the pi I over 4, which is what? 10 plus pi times b over 4. And that's equal to 20 that was given. So therefore b is apparently equal to 40 over pi. Did you guys get that? Okay, great. Then put it all together. We have phi of z is equal to 10 plus 40 over pi times the argument of z. And that is a solution to Laplace's equation on that wedge. Simple as that. And of course, I could do better here, right? Although it pains me to say do better. But if you wanted me to, I could tell you that that's the inverse tangent of y over x. Right? That's legit here. Of course, technically, this is not included because that's a problem point. But the inverse tangent does work where we are as a formula for the principal argument. It doesn't always, but it does here. Yeah. So any sector, any wedge, we can simply solve by this template. This will work for any wedge if you want to fix the values on the edge to be whatever you like. What if you want to solve Laplace's equation on an annulus? So suppose I want to solve Laplace's equation like this. So here, I'll make this, I don't know. We could make the center 0 if you guys want, but we could make it something else. I'll make it something else just to be annoying. Wait, how much time do I have? 10 minutes. All right, 0 it is. So 2, and we'll make this radius 3. All right. I'm trying to solve Laplace's equation in the annulus. And you guys can pick whichever values you'd like for the boundary. Let's make phi equal to, what do you want? 2? That's 2, radius 2. I don't want to do that. It's weird.
Let's do E.
E? You monster. And out here, we want phi equal to what? What'd you say?
We just choose any value.
Yeah, doesn't matter.
18.
18. There we go. Let's go. All right, so we're trying to solve it up in here. So what function is harmonic that is constant on circles?
Modulus?
The modulus is not, but the modulus is not complex differentiable. But you're right, that'd be nice. How do we get the modulus in something and yet have, complex differentiability? Oops, what's going on here? It's right on the board actually, right? So like, the other part of the log is this thing, right? And the funny thing about that is even though this function suffers the discontinuity at the angle jump, that does not. This was harmonic on the punctured plane. We looked at this. So if we play the same game here, we make the template phi of z equals a plus b times the natural log of the modulus of z. This is harmonic. Everywhere except for where, the modulus of z is equal to 0, right? But that's inside the annulus. We don't have to worry about that. If the annulus had instead been centered at like z naught, all you do is replace z with z minus z naught, right? So it's not much different. And then, suppose you've got modulus of z equals to 2, then you've got phi of z is equal to e, thanks Shane, which is a plus b natural log of 2. And on the other hand, if the modulus of z is 3, then we've got phi of z is equal to 18, thanks Jordan, which is a plus b natural log of 3. 2 equations, 2 unknowns. You guys eat this for lunch, right? I will take this and I will subtract these and I will get e minus 18 is equal to b times log 2 minus log 3, also known as b log of 2 over 3. So therefore b is e minus 18 divided by the natural log of 2/3. Okay, that was just extra. And a is e minus b natural log of 2, which is minus natural log of 2 divided by times e minus 18 over natural log of 2/3. There we go. So you take those 2 constants, put up in there, and there you go. And this one is done. Aw, man. Washers, wedges, and also what else? Walls. So actually, these are cool, but they're not the most profound solution to me. The cool thing is, you can also solve Laplace's equation on like a half plane. I think I'm going to do the half plane example. You guys got a homework problem on the slab. That one's easy. You'll get that from the book. It won't be a problem. If you use az plus b that solves like the component functions from like az plus b, solve it on a slab. So here is the, for half plane, the half plane solution. If I want to solve Laplace's equation, and maybe I've got like x1 here, and I've got x2 over here, all right, and so forth. All right, and suppose I want, here it is, phi of xy. I do like a1 arg of z minus x1 plus a2 arg of z minus x2 plus a3 arg of z minus x3, and this goes on, the nth one, a sub n arg of z minus xn, like that. So continuing, eventually we get to xn. All right, and you're given, so the thing is, you can write down that, and you can choose values of a1 through an to get like phi equals to, you know, let's say phi1 here, and phi equals to phi2 here, and phi equals to phi3 here, and so forth, all right? Let's see with my numbering. I don't know. Well, you get the idea. Let me stop labeling things before I get in trouble. And I think basically the thought there is to, well, he says something about like laying together half planes or something. To be honest, I haven't really quite thought through why this works, but it does. And so, like, for instance, he has this example in the book, phi of z, I'll just get straight to the point here because we're just about out of time, minus 1 over pi arg of z plus 1 plus 1 over pi arg of z minus 1. So this thing, it's harmonic on the upper half plane, and if I draw a picture, it's got jumps at -1 and 1, and it's constructed so that it's 0 for x greater than 1. Phi equals to 0 over here. It's 1 between -1 and 1. And it is 0 over here as well. But it's harmonic on the upper half plane. So like up here. So this is, of course, the real axis. And you can try it out and see how this works, right? If I put in like, what happens with this formula if I put in like 2? What's the argument of 2 minus 1? Well, what's the argument of 1? It's 0, right? What's the argument of 1 plus 1? Argument of 2 is also 0, so you get 0 plus 0 is 0, it checks, yay. What happens when I put in 0 here? If I put in 0, I get the argument of -1. Well, the argument of -1 is pi. So that gives me 1 over pi, pi over pi, which is 1. All right, then over here, when I put in 0, argument of 1 is, wait a minute, what was I at? 0, right? So argument of -1 was pi. That looks like, what? I'm confused-lated. Oh, I'm an idiot. So argument of -1 was pi, but argument, if I plug in 0 here, I get argument of 1, which is 0. Right? Because the argument of a positive real number is 0. So this 0 plus 1 is 1. Now over here, for example, at like -2, I get a -3 here, which has angle pi. So I get a 1 over, pi over pi, which is 1. And at -2, this gives me argument of -1, which is also pi. So I get pi over pi, but there's a minus. So I get -1 plus 1 over here, in the calculation. So this conspires to give me 0, 1, and 0. And the thing is that's pretty neat is, so you can solve Laplace's equation on a half plane using this trick. You can just write down multiples of shifted arguments like this, and they'll not be defined at the points where any of the arguments are 0, right? But that's where you don't expect it to be defined because there's a discontinuity there. There's a jump between like value 1 and value 0. So, and when I first saw this solution, I was just flabbergasted. I'm like, this is amazing. I wouldn't have thought it would be that easy to write down a solution to Laplace's equation that has so many different, values on the edge of something with so little difficulty. What's really cool next time, when we come back to this next week, right, is I'm going to show you how we can take these solutions. Well, really not, most interestingly, probably the last one I was looking at. I'm sorry, I was not over there. But again, this is, these things happen when we're sick, but I'm so sorry. The cool thing is, we'll talk about this method called conformal mapping next week, and we'll see that we can actually take these solutions and we can take some other complex function which will take this half plane and like wrap it around a disk or something, and then we'll be able to solve Laplace's equation on a disk where we could specify like, the value of the solution has one value on a quarter of the disk and a different value in another quarter and a different value in the other quarter. So we'll be able to paste boundary values around a disk because we can take a half plane and map it to a disk under a conformal mapping, and it just so happens that the property of solving Laplace's equation is transferred by the complex differentiable function. And the proof of that basically rests on the homework problem you're going to do and turn in Tuesday. So yay. Sorry.